Okay, so I think we're probably going to get started. So welcome everyone. My name is Nick Menicucci, and I'm from RMIT. And before we go on, based on where I'm broadcasting from in Melbourne, I'd like to acknowledge the people of the Woiwurrung and Boonwurrung language groups of the Eastern Kulin Nations. They're the traditional owners of this land, and I pay my respects to their ancestors and elders, past and present. So I would like to welcome you all to this talk. This talk is part of an ongoing series of talks for the Australian Institute of Physics, the AIP, and it's showcasing Australian Research Council Centres of Excellence. So Centres of Excellence are large consortia of universities that participate in a joint research project over a multifaceted research project over a number of years. So I'm an associate professor of physics at RMIT University in Melbourne, and I specialize in quantum information theory. If you have any questions, please ask via the Q&A window, and I will be happy to answer them at the end of the talk. The presentation portion should be about 45 minutes, and I will have some time for questions. So the Center of Excellence that I'm part of is CQC²T. That's the Center for Quantum Computation and Communication Technology, and it's funded by the Australian Research Council. So CQC²T represents one of the world's largest teams working to create a universal quantum computer and secure communication systems that rely on quantum physics. So there's over 200 researchers involved in this. We're across 7 Australian universities, and we have 25 formal international partners and 22 coordinated research programs. So it's a rather diverse, large endeavor. You can see the universities that are involved down here at the bottom. It's led out of UNSW, and there are 6 other universities that are involved. And once again, I'm at RMIT. My group, if you're interested in what I do, which includes work in relativistic quantum information, quantum field theory, a little bit of quantum foundations, you can visit Kermit.org. So it's pronounced Kermit. This is for quantum, of course. Yeah, you can find that if you'd like to have more information about what I do in addition to the quantum computing. So let's get started. So the first question that some of you may be asking is, what is quantum computing? The target audience of this talk is physicists. So I'm trying to be broad, but also semi-technical. So that will be the idea here. So what is quantum computing? Well, let's start with what is computing, or what is computation. So at the abstract level, computation is you take some input, which is information, you get some output, which is some other information. But at the physical level, what really happens is the input gets encoded into the initial state of a physical system, and the output is read out from the final state of a physical system. And in between, there's some physical process that happens to take you from one to the other. And what we do logically is we abstract all that away, and we call that computation. But computation is actually a physical process. It's this long process here, and we abstract it away to here. So the laws of computation, the laws that we can abstract out of this longer physical process, are limited by our knowledge of physics. And computations are processes, physical processes within some chosen model. So if we're only going to use classical physics, then we will derive certain laws of computation. If we're aware of, and classical means Newtonian physics. If we're aware of quantum physics, then we might derive other laws of computation. And that's exactly what happens in the case of quantum computing. Computations are constructed from a small universal set of gates. These are elementary operations. Now, there are some models of computation that don't do this, but the ones that we'll be talking about today are essentially you want to be able to implement elementary operations, and then you put them together, and the set is such that you can combine them in a way to do whatever computation you want. I'll get to a little bit more about that in a bit, but first I want to now specialize to quantum computers. So quantum computers are, quantum is notoriously enigmatic. 2 excellent words there. But quantum computers basically harness quantum physics to compute in a completely new way. And why do we care? Well, it's because quantum computers can do some computations, some important computations, faster than any ordinary computer is known to be able to do them. So for instance, here's a simple example. If multiplying is an easy operation. So small multiplications you can do in your head. 3 times 5 is 15. Larger computations would be difficult for most people to do in their head, including me. I can't do this in my head, but I could do this with pen and paper. It would be annoying, but it's the kind of thing you'd do in primary school. But certainly you could do it on a computer or a calculator or your phone. Factoring is also easy for small numbers, but it gets very hard for big numbers. And you can just punch the numbers in the calculator and get this immediately. And you can do this for many, many digits. You can have hundreds, thousands of digits, and your computer can do it almost instantly for multiplication. But if you have thousands of digits in a large number and you tell the computer to find the factors of that number, find the smaller numbers that multiply together to give this one, that's going to take a long time. That's much harder to do for an ordinary computer like your desktop or your laptop. However, factoring is easy for quantum computers. So this was the original killer app of quantum computing. This is Shor's algorithm. It's by Peter Shor in the 90s. And he came up with this, and suddenly governments were stunned, because if you can factor quickly, then you can break public key encryption. And public key encryption is essentially all the encryption that's used to secure your purchases on the internet and to secure any kind of secure communication between devices. It's a lot of it is based on public key encryption. And the idea is you can share a public number, which is like a big number that needs to be factored. So if you can factor the big number, you can decode the encrypted message. And the idea is it's hard to factor big numbers. And so you can share the big number so that someone can encode their message, and then only you can decode it because only you have the factors of that number. But if it's possible to factor quickly, then that security goes away. So that's quantum taketh. Quantum taketh away, but quantum also giveth, in that quantum simulation is the use of quantum computers to simulate other quantum systems in an efficient manner. So this is expected to lead to new material design, new drug design, and this is going to be quite a positive good. So there are security implications, and there are economic, health, industrial implications as well. So how do they work? Well, let's start with quantum bits. So quantum bits, or qubits, are quantum systems with 2 addressable states. And we'll call these states 0 and 1. So it could be the up and down spin of an electron. It could be the ground state and some excited state of an atom. Whatever it is, we're just going to label them 0 and 1. So we call that the computational basis. And quantum computers process qubits instead of processing regular bits like the ordinary computer does. However, qubits can be in a superposition of 0 and 1. So what does that mean? Well, first of all, superposition is not both 0 and 1. And I mean, I get some pushback from other physicists on this. And the reason why it's a good analogy is because there are aspects of both. We'll get to that in a second. But it really leads to bad intuition. And the reason it leads to bad intuition to think that it might be both 0 and 1 is that you only ever get one bit of information. In other words, one outcome out of the 2 when you measure a qubit. This is a bound known as the Halevo bound. It limits how much information you can get out of a single qubit. And that's really important because you might think, oh, I have all these different superpositions, and so I have way more information there than I actually do. Well, yes and no. So it's not both 0 and 1 in a naive classical sense. But it's also not either 0 or 1. So there's some randomness when you measure a qubit that's in superposition. Sometimes you get 0, sometimes you get 1. But that doesn't mean that before the measurement, it was either 0 or 1, and you just didn't know it. That too is incorrect. Why is that incorrect? Well, it's because large superpositions can be manipulated so that alternatives interfere like waves do. It's not just for large superpositions, but I put large here because that's where the real power is. So So in the case of a mixture where a probabilistic mixture where you have one or the other and you just don't know which, well then you always either had this one or this one, you just didn't know. So you can move that uncertainty around. But with quantum superpositions, you actually have the ability to have these manipulate these alternatives such that you get interference. And I'm not going to go into the details on that, but that's really important, that you can get interference effects, which is not something you can get with, say, flipped coins or things that are classically random. Okay, so qubits can be in superposition. So what? How does that help? How does a computer actually work? Well, the answer is basically, you might think this. For those of you familiar with gnomes, phase 1, create superposition. Phase 2, phase 3, the right answer appears. Okay, well, it might be nice to have a little more detail in phase 2. Okay, so first of all, do quantum computers do all possible calculations at once? Is that phase 2? No, it's not phase 2. That is not how quantum computers work. Do not let anyone tell you that that's how quantum computers work. That is misleading. So let's see why it's misleading. So they work by step 1, phase 1, create a superposition of many possible solutions. This is basically what they do. Although, again, you can quibble over this, but this is the basic idea. You create a superposition of many possible solutions, and then you manipulate the superposition so that wrong answers cancel out and right ones are strengthened. And that means that in the final step, when you measure the qubits, you're likely to get the right answer. That's how it works, more or less. It's this second step that is really important here, because the need for the second step means that quantum computers are only advantageous for certain specialized problems. It is extremely fast to create a superposition of many possible solutions. If you had a very low noise, high quality quantum computer, you could do this extremely fast. And then, you say, oh, well, if it was really all the solutions at once, all possible calculations at once, then you'd say, oh, well, we're just done. We can just get it out, phase 3. But it's this part. It's this part that takes time, and is this part that can only really be done for certain types of problems. And I'm not going to get into exactly which types of problems because that's a whole other research question. But the important thing is that quantum computers are not just generally fast because of this. And they don't do all possible calculations at once because of this second step. All right. So once again, quantum computers can do some computations faster than it is believed that any classical computer can do them. And by classical computer, I just mean ordinary desktop laptop. I gave 2 examples, factoring for code breaking and quantum chemistry, quantum simulation, essentially, new drugs and new materials. There's 2 main challenges. Again, you could quibble with these, but there's basically 2 main challenges. One is the precision of the calculations. You want to minimize error. You want to minimize noise, environmental decoherence, as it's called. And you also need scalability. You need these devices to be large enough so that they can do something useful. Taking the factoring example, if you build a machine that can factor 15, that's great, but it's not going to be able to do anything that a human being or an ordinary computer couldn't do. So it's great for prototyping, but not so great for applications. And there's a bunch of possible implementations of this. So experimentally, there are superconducting qubits, there's optics, there's trapped ion qubits. We have nuclear electronic spins, quantum dots. And theoretically, there's a number of models as well. So there's the circuit model, which I'll show in a minute. There's the cluster state model, which I'll show as well. And then we have quantum bits, qubits, quantum dits, which are d-dimensional systems. Like you can use the ground state and 2 different excited states. That would be a q-trit for 3. If you have d of them, that's q-dit. Or quantum continuous variables. So these are all possible for use for quantum computing. In terms of the experimental setups, there are reasons. I'm going to focus on optics in this talk because this is what I work with. And there are a number of reasons why advantages that optics have. The main one is room temperature operation. That is the really killer advantage of optics over other systems currently. Although you could argue that some systems also have this nanodiamonds perhaps, but in any case, optics is room temperature. the superconducting devices that have made a splash recently all have to be in a fridge, meaning a dewar that's vacuum sealed and pumped down to a very low temperature. So optics doesn't have that issue. That's the main advantage. But we'll discuss a few others. I'm going to focus on scalability in this talk because the work that I've done and the work that I'm going to showcase today is really all about scalability. We and everyone else still needs to up the precision of the devices that we have. So the idea for some of the architectures has been to build small devices very well and then scale them up. In this case, it's more of a let's scale it, show that we can scale it first, and then we will work on the precision. All right, so let's talk about transition to the actual nuts and bolts of this. So qubits and continuous variable systems. So let's go back to this. We said at the abstract we have an input and the output. These are just information, but of course they're actually physical systems. And in between we do a quantum computation now. What does that mean? Well, here's what it means. Remember that a computation is just some physical process. So the input is, if it's encoded in a quantum bit, we can represent the quantum bit by a vector on the Bloch sphere. If you have multiple quantum bits, qubits, which you'd need for a meaningful quantum computer, then the diagram doesn't work anymore because the Hilbert space is weird. But for a single one, you can draw it like this. And at the output, you have it in some other orientation. The qubit has changed. And in between, there's a unitary evolution. So this is just standard quantum evolution, whatever it is, but you need to be able to do whatever unitary that you want on a single qubit, or more usefully on multiple qubits. So you have a quantum computer with 1,000 qubits. You need to be able to manipulate those qubits coherently and precisely so that they start in one state and end up in some other state that you control from the outside. So what is with these continuous variable systems? Well, I mentioned some examples of qubit systems. An example of a continuous variable system would just be the position of a very tiny particle, or a very cold particle, really. Could be any size if it's cold enough. But the position of a quantum harmonic oscillator, for instance, or maybe you have a tiny little nanomechanical resonator and it just vibrates like that. Its displacement from equilibrium is a continuous quantum variable. Another one is the amplitude of an electric field mode. So you have a cavity and then there's some field modes within it, some optical modes, and the electric field oscillates inside the cavity, and the amplitude at some particular time of that oscillation in some direction is a quantum continuous variable. So if we talk about quantum computing with continuous variables, what we're saying is we start with some wave function for a continuous variable system, and we evolve it to some other wave function. So in this case, this wave function has been displaced. Maybe you have an oscillator and you do something to it so that it moves some amount downward. You can do this optically as well. You can change the electric field amplitude in a field mode. I'm not going to get into how, but you can ask in the Q&A if you're interested. Let's talk about cluster states. So this is, let's just jump in. So I like to talk about this as teleportation light. So some of you may have heard of quantum teleportation. I'll show that in a minute. But this is light in the salad dressing sense. This is a word that's added to various condiments in the U.S. primarily. I don't see it here very much. But anyway, it's spelled L-I-T-E because it's lighter than having the GH in there. It's, low fat. Anyway, whatever. Okay, this is a quantum circuit. This is the kind of diagram that we use in the work that I do. So I'm going to break this down for you. If you know what this is, then that's good. You can make a connection between that and what I'm going to show. If you don't know what these things are, then I will tell you all that you need to know about them, and you don't need to understand them in detail. What's important is that I'm going to develop a graphical representation of this and a graphical manipulation of these sorts of things here. So we're going to start with the quantum information that we care about. So this is going to be represented by this gold disk here, this gold node. So this is a quantum state. Quantum states are fragile, they're precious. That's why the gold here. This is another quantum state. It's an equal superposition of the 0 state and the 1 state in whatever basis you choose. And this is going to be represented by a blank node. It's not an unknown quantum state. It's a very prescribed one. It's just blank. Now this gate, this is a quantum gate. This is a two system quantum gate. So this entangles the two individual systems. And this is a C phase gate or a controlled Z gate, depending on your terminology. But what's important is we draw it as a line between these two things. These are individual gates, which is just unitary interactions on individual qubits. And this is a rotation about the Z-axis in the Bloch sphere. And this Hadamard gate is a 180-degree rotation such that the up-down and the sideways axes are switched. That's the Hadamard gate. And this is a measurement in the computational basis. But we can do them all together. And all together, we can just say that this is a measurement in some axis in the equatorial plane of the Bloch sphere. And you get some outcome. If it's a qubit, you get, well, that's what this is. You get some bit, either 0 or 1. And so what happens when you make that measurement here is that the output state is the same as the original input state, except some quantum computation has been done to it, which is represented by this. Now, this may not seem very exciting. We didn't do very much, but it's really subtle and it's really important how this works. So notice that this H is fixed. This always happens after this gate. But this alpha is a parameter that you can control. So in other words, I like to think about it like this. So as a quantum system, there's more than one measurement I can make on it. So I can choose to look at a system and measure it along some basis, or I can measure it along some other basis, or I could, well, those are the choices really. And so I get to choose how I turn my head to look at this object. In a lab, it would be some measurement setting, some dial that you would dial in to make a particular measurement as opposed to a different one. But the choice of measurement that I make here, I should say here, the choice of measurement that I make here actually shows up as a quantum gate that has affected this quantum information. And so that's really cool, because it means that simply by how I choose to turn my head determines what quantum gate I've done through the measurement. So this is known as measurement-based quantum computing. This is one step of it. Importantly, though, you need to know what this outcome is. This is not magic. As in, if you don't know what this outcome is, then you lose the quantumness of the state at the end. But if you do know what the outcome is, then you know what happened to it. Whether then this is just a 180-degree flip about the x-axis of the Bloch sphere. So at the end, you get the same state out with some modification to it. And importantly, depending on how you measure it, so indicated by the direction of this line, different things happen at the output. All right, that's really important. So let's talk about regular teleportation. Regular teleportation, as first discussed, starts with some quantum information that you care about, and then you create this entangled pair. So you start with these blank nodes, you create entanglement between them, and then we make a particular type of measurement on these two. And what happens is the information gets teleported to the other side. So this is used as a communication channel. And importantly, depending on, I mean, it doesn't matter how far away these things are. In principle, if you can protect them, you create the entanglement locally, and then you can move one way far away. And the way that we're going to do the measurement is to first entangle these two and then measure locally. And what happens is the quantum information gets teleported over here. Now, in order for the person over here to recover that information, you need to tell the person what the measurement outcomes were that you got. But anyway, it's there. Let's go back a step and just look at this. This was the original entangled pair. This is additional entanglement before the local measurements. And because the two measurements are local, we can do them in either order. So for instance, we can measure this one first, in which case the information hops, the quantum information hops one step here, such that when we measure it again, it hops a further step down the end. Let's do it in the other order now. So we know that if we measure the middle one first, and then the one on the left, it still has to hop over here. So that must mean that the first measurement, it pops out this qubit, and now we have these two things that have entanglement generated between them. So we've learned a new rule here that if this one is in between two others that are connected to it, then you could pop it out by measuring it, and you have induced entanglement between the two ends. So now when we measure this one, it hops to the end. All right, why do we care about this? Well, one thing is we now have two dials to turn. We have two different measurements that we can make. So if we choose to make repeat the experiment with a different measurement setting, then something happens to the quantum information. And similarly over here. And so if we do a big chain of these, we can do whatever we want to this quantum information. So as an example, this is a teleportation network. So in this case, we can imagine that there are two states that started here and here. And we're going to make measurements on them, manipulating the information as it goes, and down here, manipulating the information as it goes. And then how do we get these two things to talk to each other? How do we get them entangled? Well, we get them entangled because there's a line vertically here. So we want this one to become entangled with this one. And so what we can do is we can measure the one in the middle. And that creates this entanglement. And then we can keep measuring and keep pushing the information along until the end. Now, why was that important? That was important because the previous pictures that I had was only manipulating one quantum bit of information. But I said earlier that we need to put a bunch of these quantum bits together. And if we're going to put a bunch of them together, we need a way to get them to interact with each other. So we need to do that by the structure of the entanglement in these states. So the canonical state for this is called the cluster state. So you can see that this is just a recipe for making a big state. So you start with a bunch of these blank nodes, and then you do these particular quantum interactions between them, and you can create this resource for quantum computing. And so again, what we have here is you can kind of see that we've got this teleportation network that is embedded within this cluster state. And it's just we have these extra things that are hanging around, kind of getting in the way. There's a different measurement that we can make that actually measures these and deletes them. It separates them from the rest of the ones that are not measured. And now we see that we have exactly the same structure as before. So now I can get these qubits to evolve, we can manipulate them, and we can get them to interact with each other through this cluster state, all by using just measurements. That's what's cool. So if you start with a cluster state, then all you have to do on it are measurements to do quantum computing. And that's what you get. All right, so the idea for this is from 2000. It's a one-way quantum computer, and one-way just means single use. So the authors wrote, we present a scheme of quantum computation that consists entirely of one qubit measurements on a particular class of entangled states, the cluster states. Now this is important. The measurements are used to imprint a quantum logic circuit on the state, thereby destroying its entanglement at the same time. Cluster states are thus one-way or single-use quantum computers, and the measurements form the program. Cluster states are one-way quantum computers, and the measurements form the program. So this is a diagram from this is a figure from their paper, and this represents the way you turn your head to do the various measurements on each of these qubits, so that you evolve the qubits, you manipulate them, you get them to interact with each other, and at the end, you've done some quantum computation. Remember, we start with some qubits, we need to be able to manipulate them in a controlled fashion and get them at the end. That's what this device does, all with just measurements. Okay, measurement-based quantum computing. So there is a continuous variable analog of these cluster states, and it was developed in 2006. So these folks came up with the idea for the state, and we showed that you can use them for computation. So this is when I was at University of Queensland. So the optical implementation of this is more for specialists, but I will just tell you anyway. For any harmonic oscillator that you might write down, you have an A operator and an A dagger operator. And if you add them together, you get a position operator, and that has a continuous spectrum. And so when we talk about a computational basis for continuous variable systems, what we mean is the position of it. And remember that when we're doing quantum computing in a continuous variable sense, we just need to be able to you start with the wave function for some system and you change it into some other wave function in a controlled way. And so the basis of numbers that we would choose for that, the computational basis or eigenstates of the Q operator. There's also a conjugate basis, which is eigenstates of P, which is the conjugate quadrature for those who care. Advantages of continuous variable over qubit cluster states, at least in the optical domain. Well, it's deterministic generation. That means that you push a button and these things just come out. That's not true generally when you deal with optical qubits. It's also scalable to huge sizes. And again, if we want to have if we want to process information in a useful way, we need big states. But there's a problem. The CV cluster states, which I didn't describe in too much detail, in fact, I haven't described them in detail at all. I've just said that they're the analog of this, but all the basic rules apply. The problem, though, is that ideal ones would require infinite energy. So you can't even talk about them being makeable with any equipment. Even if the equipment were perfect, you still could not make them because you only have finite energy resources. So because we only have finite energy, this leads to noise or errors in the computation. Now that may seem like it's a showstopper, but it's not, because quantum error correction is a way of figuring out your best guess of what error happened to the information and correcting it. Sometimes you fail, but then you correct that error too. And if you can do that in a way such that small amounts of noise can be reduced, then that's called fault tolerance. So let's talk about this. So in 2001, there was a paper that showed, well, let me take a step back. If we're going to talk about correcting errors, think about digital audio versus analog audio on a cassette tape. I was around when there were cassette tapes. Some people watching this may not have been. But the idea with a cassette tape is that you encode the audio signal in the actual amplitude of the, you encode the signal directly into the physics. Whereas in modern digital encodings, you encode the signal into digital data first, and then you store that data as a file on a device. And so the digital part of it is really important. So in this case, we need to put our qubits into these continuous variable systems. What does that mean? It just means that we choose some wave functions that represent our 0 and our 1. So for those of you who recognize this, this is the wave function for some continuous variable system. And the blue line here is the 0 state, and the red line is the 1 state. If you don't know the details of this, it's not all that important. What is important is that there's these two different wave functions for some quantum system. Okay, so what happens if we send this quantum information as this gold piece here? What happens if we do that? Well, as it propagates through via measurements, remember, we're just going to make a measurement here, the information hops, and then it hops as each time you make a measurement. Well, what happens is it acquires some noise. It decays a bit. You can see that you start with what is a superposition of the 0, which are these even spikes, and also the 1 state, which are these odd spikes. And so it creates this pattern where it's mostly the spikes are on the even grid points here, but some of the wave function is also on the odd grid points. But over time, it just kind of decays as you make measurements and the information flows down this line. So what we can do, though, is we can stop the process here. And if we do that, and we do a particular quantum circuit that I'm not going to describe, but if you have a resource state that allows you to measure the decay of this state, then you get some outcome, and it tells you essentially, it gives you a better quality state. Look at the spikes here. These spikes are narrower than they are here, and that's a better quality state because the spikes should be very narrow. So you get a better quality state with narrower spikes, but it's off grid. You can see that it's not aligned with this grid anymore. So before we had these things that were aligned with the grid, but they were kind of crappy. Now we have a state that is not aligned with the grid, but it's a better quality state. So the outcome here tells you how far off grid you are. And then you have to put it back onto the grid. You have to displace it. So if you choose to displace in the correct direction, then you get no error, in which case this tall spike is still at this, this middle location. So the tall spike matches up. Remember, you don't know what the state is. So you just have to make a guess based on this outcome. And if you guess correctly, then the tall spike moves back here and that you're good, there's no error. But if you guess incorrectly, like maybe you think it's closer to having come from a spike being here, then you have an error at your qubit that you've encoded into this system. Well, that's okay, because fault tolerance says that those qubit level errors can be corrected. So remember that measurements implement these gates. They're a little bit screwy, they're a little bit noisy, a little bit faulty, but that's all right, because we can use qubit level quantum error correction to reduce the errors. I'm not going to go into that. If you have questions, you can ask. It's well established. Fault tolerance says if the initial error is low enough, then you can smash the error to 0 in your final computation. And I showed that this was possible in 2014. So for the final portion of the talk, let's talk about making CV cluster states. So one way to do it is to use something called squeezed light. It's a laser on a nonlinear crystal and a beam splitter network. So these are individual squeezers, and this is a network of beam splitters. So this was demonstrated more than a decade ago, and it does work. The problem is that you need a different one. You need one of these for each of the individual nodes in that graph. And remember, we want a big graph because you need to be able to process information over time and to process lots of quantum inputs. You need a large cluster state. So this is not great for scaling up. So how do we make a scalable resource state? Well, the basic principle, the basic structure of the state is slightly different than I showed you before. So when we started with just the line of nodes, we just had one node connected to one node, connected to one node, all the way down the line. Here, we're actually going to have two nodes that are connected in this fence-like pattern. But if you kind of zoom out and you look at it, it is just a line. It's this sort of, fence-like structure between them. That's all right. It still functions qualitatively the same way. But importantly, each black dot in this is either, depending on the model, and I'll show you both, a specific color of light. So this might be red, and this might be slightly oranger, and this might be more toward yellow and toward green, etc. Or it's a pulse of light. So you have a laser, and it's creating little pulses over time. And so this might be, let's say, 2 laser beams, and this would be, at time 0, time 1, time 2, time 3, etc. And the edges represent entanglement. You can get larger structures like this, like a cylindrical state. And if we zoom in, we see that there's 4 of these dots per macro node. But nevertheless, if you look at the structure of this, it looks like a square grid, and it is. So remember that the cluster state we want to make is a big square grid of these things connected together. We have that with the caveat that each of the nodes is actually 4 individual modes of light. That's all right, we can still use it. So I'm just gonna briefly touch on a few experiments that have been done in the last 6 years on this technology and how far we've come. So frequency mode or color-based cluster states. So in 2014, the Olivier Pfister, his lab at the University of Virginia came up with a 60-mode linear cluster state that looks like this. So it is exactly this type of state. And that was quite big for the time. 60 individual quantum systems all entangled with each other. That was impressive. Here's a picture of their setup. They use green light, and the green light hits the optical parametric oscillators, which are these crystals in cavities, and what comes out is infrared light, so you can't see it. But the basic idea is that you start with what's called a pump, which is just a laser coming in. It hits this optical parametric oscillator, which is just this crystal in between 2 mirrors, and out pops a cluster state whose nodes are different colors, and they're all entangled together. And then you need to do frequency-sensitive measurements to measure it and use it. But notice that the setup for this is relatively small. You have 60 modes of light, and you have a tabletop experiment, room temperature. Temporal mode, or pulse-based cluster states, came shortly thereafter. Actually, sorry, this was actually technically before. So this was a 10,000 mode linear cluster state out of the University of Tokyo, Kira Furusawa's group. 10,000 modes, all entangled together. This is huge. This is mammoth-sized cluster states. And this is the experiment they did it with. This is, again, a tabletop experiment. You know, it's probably maybe twice my arm span, maybe 3 times my arm span. But it's a relatively small experiment. It fits in a lab, and it's room temperature. And so the key pieces are, you've still got these special crystals within mirrored cavities. You shine light on them, and out pops these pulses of what are called squeezed light. And then there are just a few little beam splitters. So you have a half-silvered mirror that splits the light between it. So some of it gets reflected and some of it goes through. And then we just have a long fiber delay on one side of this, another beam splitter, and out pops this state. This is very cool. It's a very simple design, and you get a very large state out of it. Here's an animation made by my colleague Seiji Armstrong. This is available on YouTube if you want to see it after this talk. But here we have pulses of squeezed light represented by these yellow blobs coming out. After squeezed light passes through a beam splitter, it becomes entangled. These lines here are similar to the lines that I showed before. The time delay makes this node here, down here, match up with the other node of the next pulse, so that when it goes through the next beam splitter, it doesn't get disentangled, it gets further entangled into this fence-like structure. And then they just measure it here, and this is how the measurement-based quantum computing would happen. This is the diagram of their experiment. This is the key point again. You've got your beam splitters and just some fiber delay in between. It's an unbalanced Mach-Zehnder interferometer. That's all it is. In 2016, they outdid themselves with a 1 million mode linear cluster state. Still the same line, but a million modes. Very impressive. And just this year, they demonstrated a prototype of measurement-based quantum computing with this system. So this is very exciting. They actually did, they changed the measurement bases that they were doing, and they actually showed that they could do quantum gates on the information that was encoded in this state. So that is very impressive. That's with referees right now. Same group. I've been working with them. Last year, 2 groups, both the Tokyo group and Ulrich Andersen's group in Denmark, we published a demonstration of the 2-dimensional cluster state. Everything I've said before was just linear, and so you can only process one piece of quantum information as it goes. And remember, we need a big square grid so that you can process multiple things and get it talking to each other. Well, so this is this is our design implemented in Tokyo. You can kind of see similar things to what we had before in this setup. These are the optical crystals in little cavities. Here are the pulses of squeezed light that come out. Here are the beam splitters, except this time there's a few more beam splitters and there's 2 delay lines instead of 1. If you want more information about this, you can have a look at the paper or ask questions. But what comes out is this. And this is very cool because now you can see that we have this square grid structure. In fact, this part here is zoomed in. And what you have are 4 individual modes per macronode. So the overall entanglement structure is like this. It's a square grid. But at the very fine-grained level, you have 4 individual modes. And they correspond to the 4 beams, a pulse of light, 1 in each beam. That gets entangled into this large cluster state. And we showed in the paper how it could be used for quantum computing. The Andersen group did a slightly different design. They have a fewer number of beam splitters, just 2 of these optical crystals, but it's still this same. Well, it's not really the same, but it's a little bit different, but it's basically the same idea. You have a 2-dimensional graph of information. Importantly, though, each of these individual dots that gets woven together like this is not being woven in space. This is not a big spatial thing. It's just the logical connections between different pulses of light in different beams. That's what this graph represents. That's also what this graph represents. We didn't make an actual object that looks like this. This is the logical entanglement structure of this. What's really happening is you just got a bunch of light shining into these things. And so you end up just measuring these things as they go around. Same thing here. So what's missing? Well, the quality of these states is too low. And that's measured in something called squeezing. And the amount of squeezing is too low. Ask me if you want to know details. There are also tabletop experiments. They're still quite large, and they almost certainly will need to be miniaturized to reduce the noise even further in order to achieve this. So we need to put them on an optical chip. And these states that I talked about, these qubit states, these are Goddess-Mikitaev-Preskel states, GKP states. These are hard to make. They've been made in trapped ions and in microwave cavities, but not in optics yet. And so when I was talking about the handling of errors, that all relied upon the processing of these particular types of encoded states. So these states are like the train cars that will ride on the network of rails that are these cluster states. So this is like the train network, and then what rides on them are these GKP states, which are very hard to make, and they haven't been made in optics yet. So this is what's missing. This is why we don't have a quantum computer yet. But in conclusion, I'll just summarize. Quantum computers, they harness quantum physics to do some computations very fast. They don't do all computations at once. That's an oversimplification to the point of being incorrect. They manipulate superpositions in a clever way so that you can get the right answer in a shorter period of time than if you had a regular computer. Continuous variable cluster states are a particular type of this cluster state. It enables quantum computing using measurements only. And it's measurements in this case of quantum continuous variable systems. Fault tolerance is possible. The handling of noise is possible if you use quantum error correction. And this is an important thing. This is a big question about 20 years ago. Like, does the detailed nature, the fragile nature of these quantum systems just totally screw you up when you try to use these systems for computing? But no, it turns out you can actually do quantum error correction. And then we demonstrated some experimental methods that are shown to be quite scalable. We have a one-dimensional cluster state in both frequency and temporal modes, and a two-dimensional one in temporal modes. Millions of modes have been entangled together, and they in Tokyo demonstrated measurement-based quantum computing prototype of that. We need to improve the squeezing, and we need to make GKP states. So that's it for my talk. I'll take questions now, but before I do that, I would just want to advertise next month's talk, the 4th of September. The ARC Center of Excellence for Exciton Science will be presenting. This Center of Excellence studies and manipulates the way light energy is absorbed, transported, and transformed in advanced molecular materials. So the talk will be given by my RMIT colleague, Dr. Nastaran Meftahi, and she will present a shortcut to property prediction for photovoltaic materials through machine learning. So that's it for me. I'm happy to answer questions. And I realize that it'll take a while for people to type their questions and get that going. But it looks like we have already some, excuse me, get some water. Okay, so we already have a couple questions. I'll just get started. So let's see here. I don't know if that works. So the question is squeezed light at the input a necessary condition in order to implement cluster states? If yes, why? For continuous variable cluster states, yes, it is. And the reason that it's necessary is because we want to use, well, it's a good question. How do I explain this? It's the simplest non-classical resource. So if you want to do something with quantum, you need something that is not easily obtainable straight out of the box. So like a laser just produces a state that is not immediately usable for quantum computing. It's just the way that entanglement works in continuous variable systems. The easiest way to make it is often to take a single laser beam and you send it to the crystal, you get squeezed light. You put it together with another one in a beam splitter and you get entanglement. So squeeze light is the source of the entanglement. When you send it through a beam splitter, that's what you get. If you want to follow up, please do. But that's basically the answer. So let's see, here's another question. If you are making this cluster state in the time domain and measuring the pulses as you go, then would that prevent entanglement between pulses which do not exist at the same time? Good question. Let's see here. How do I explain this? Will it prevent entanglement between? Okay, so If you measure too early, yes, but we don't. We design the system so that hopefully you can see the screen. You have to create the entanglement with the next layer of pulses. So this is actually like a threaded spool, if you will. So you create all these pulses, and then you wait. That's what this time delay is for. That's why the time delay is there and why it has to be much longer, because you have to wait for all these things to come out before you connect them up next to their neighbors. But once you connect them up to all the neighbors as required by these beam splitters, then you can measure the original layer. So you're basically just creating one layer at a time, and you're measuring each as you go. One other question. How many people are working on quantum computing in Australia? Well, that is a good question. So let's see here. Over 200 researchers. It's probably more than that, because that's just CQC²T, and there's other people who are working on quantum computing that are not in CQC²T. So I would imagine, probably 300, roughly. That would be my guess. Okay, so here's another question. Josh says, progress is amazing. Thank you, Josh. What do you think the next landmark or big challenge is for the experiments? All right, so let me go. That would be this question of what's missing. So there will be landmarks in terms of amount of squeezing in these states. There will be landmarks in terms of making these states on chip. And there will be landmarks in terms of making GKP states. So there's really 3 that will happen at some point soon. Okay, so we have another question. Have there been commercial spin-offs on the way to quantum computing? Yes, there have been. So there have been a number of them. So heaps. I didn't go into that in this talk. There are other people who are better positioned to talk about the state of the industrial setup, but I can talk about the ones in optics. So the ones in optics that you'll hear about the most, as far as I'm aware, are PsiQuantum. That's out of Silicon Valley. And this is working with photonic qubits. And so they're a startup that's trying to make qubit-based cluster states. So they're still optical, but they don't use the procedure that I discussed here. They use single photons representing qubits. So if you have two modes of light, let's just say 2 polarizations. So you have a horizontal polarization or a vertical polarization. And if your photon is horizontally polarized, then it's a 0. And if it's, horizontally polarized, it's a 0. And if it's vertically polarized, then it's a 1. And you can create superpositions of it, and you can get them to go interact with each other. The tough part about photonic qubits is that getting the photons to talk to each other, to interact, to entangle, is very hard. And it's hard to the point where it's not deterministic. So you try to do the entangling, and it just doesn't work. Sometimes you just lose your state completely, or you lose that piece of the state. And so you have to have a lot of machinery to put it together. PsiQuantum is working on that. The other company, which I am helping out with, full disclosure, is Xanadu, and that's out of Toronto. And Xanadu is working specifically on continuous variable approaches to quantum computing. So they're working on a variety of approaches. Some of them are related to this, and some of them are a little bit different. Some of them are more general, and some of them have been innovated by the company separately. So yes, there have been, and these are not the only ones by any means. So we've got a couple minutes left. If there's any other questions, I don't have any others in the list. But if there's any other questions or follow-ups, feel free. Looking like we might not get any further questions, but I'll give people just another second. Still got time. I have to admit, this is becoming more routine to give talks like this. It started very good. It started very weird, but it's becoming a little bit better. Oh, here's one more question. Let me see here. So the question is, has encryption already been broken using quantum computing? If not, how long do you think before that may happen? Okay, that is a very good question, a very relevant question. Practically speaking, no, encryption has not been broken by quantum computers. And okay, encryption has not been broken by quantum computers. And the reason is the computers that we have are either too small, too noisy, or both. And so we don't have anything that will screw with your data right now. However, in the next 20 years or so, it's going to be a significant possibility that that might happen. And so if you're going to be creating security protocols, for instance, for secure communication between banks, like the SWIFT protocol, that needs to be secure against quantum computers, because you don't want to have to change those things every 5 years. You know, you definitely don't want to have to change those things as soon as you discover that there's a quantum computer that is noiseless enough and is big enough to do some damage. You want to be able to just have it already secure. So this is why post-quantum cryptography is already being studied at the regular classical computer science realm. So no, it's not immediately a problem, but we already need to start thinking about it. Okay, and the last question is for the slide up now. What point are you going to be thinking about hardest next? So I'm working a little bit on all three of these, but I'm actually working a little bit more on the theory of how these things are used, because these are more technological challenges. So I'm assisting people with them, but really the main part of my work is going to be, how can we get around some of these problems? How can we reduce the amount of squeezing that's required? We probably won't be able to get it down to what we have now, but something a little bit less onerous. So something on the 10 decibel level rather than 15 or 20. So I think that's going to be it. And because it is noon, we just ticked over. So yeah, so Errol just said, thanks everyone for questions. Thanks for attending this talk. And yes, we will see you next time.